So, now that we have multiplying and dividing by integer numbers under our belt, let's see how we can expand our notion of number to fractions. Remember how we drew 3 dots and initially the meaning was, well, this is 3. And then we noted that this also has the meaning of plus 3, add 3, and then we figured out how to revert the operation of adding 3. It was taking away 3 by 3 antidots. And this was no longer an operation, but a standalone number. Now we do the same with copying machines. So we consider a copying machine like this as standing for the number 3. And now we ask, how can we operate on the copying machines themselves? How can we add and subtract, multiply and divide these machines? Of course, this also requires to consider the opposite machines, dividing by 3, also as numbers, and we have to make sense of how they work. Okay, let's start with the simplest case of adding such machines. Let's go back to a multiplying machine times 3, and then let's say we have a different machine here that multiplies by -4. And we ask, what is the sum? Well, the sum is most naturally the idea of we put something in here, get 3 copies, we put the same thing in here, get -4 copies, and we actually want both together. So we just consider a single input and want back the sum of these. And we already see a lot of cancellations. So actually these 3 here can be cancelled with the 3 anti-copies here. So effectively we have just multiplied by -1. So this is just the distributive law in disguise. I leave it to you to figure out how to subtract one machine from the other. Now let's look at multiplication. What sense does it make to multiply this machine with this machine? The idea of multiplication is to say, well, we make 3 copies of something and then we insert this into the other machine and make 4 negative copies of these 3 copies. That is what multiplication is, and we've seen this also in this array notation. So we imagine 1 here, we make 3 copies of it, and then -4 copies of these 3 copies, which amounts to first making -4 copies of 1 and then 3 copies of that. So that is multiplication of these copying machines. But we've also seen the dividing machines, so going the other way around, and we now try to make sense of what it means to multiply these machines with each other. Actually, let's start right here and ask, what about these 2 machines? Divide by 3 and divide by -4. So we actually have the answer already down here, because this is division by 3. And downwards we have division by -4. And the overall effect is obviously to divide out -12. So this dividing machine times this dividing machine is most naturally a dividing machine that divides whatever it is given into -12 equal parts and then take out a single part. In classical algebraic notation, that would be 1/3 times 1 over -4 is 1 over -12. So we've seen that a dividing machine that takes whatever it is given and splits it into a different parts and then retains a single part. This we note as 1 over a. So multiplication by 1 over a is the same as division by a. And I leave it to you to find the visual illustration of this law for which we've just seen an arithmetical example. Now, we've seen how we can multiply multiplying machines with each other. We've seen how we multiply dividing machines with each other. What happens if we take the machine that divides by 3 and multiply it by the machine that multiplies by 5? The rule is still the same. Whatever is the result here, put it in here. We could also argue the other way around, but it seems to be more fitting to use this version here, to say we have a single copy as output here. Let's put it back in here. So we actually have this here. So we are looking for 1/3 times 5, or 5 over 1 if you really want to see what is happening here. This is 1/3, 3 copies of something and we retain a single copy, and then we make 5 copies of that. And as soon as we see this, it kind of seems superfluous to have this middle single copy, doesn't it? The rule is just to take whatever you have, divide it into 3 equal parts, and then retain 5 of them. So this is the multiplication by 5/3. Well, we have to check that the other order of the multiplication works as well, and it has again a slightly different visual representation, and that would be the following. What if we take 5 over 1 times 1 over 3? So we take the machine that makes us 5 copies of something, and then this result gets divided into 3 parts, and this is a bit, well, if we want to put this into a machine that divides by 3, but it's a bit weird to divide this into 3 equal parts horizontally, but we don't have to do it horizontally. We can perform this division vertically and say the arrangement of dots that we put in here, we actually divide it vertically into 3 equal parts and retain just a single one of them. So what's happening here? This division by 3 that we've performed here mirrors back here. So this was 1 unit and we put it into 3 parts. So what we actually did is we took the original, divided into 3 equal parts, and then we multiplied by 5, giving us 15 parts, and then we retained only 1/3 of those, that is 5 parts. So what did actually happen? We had something that we divided into 3 equal parts, and then we retained 5 equal parts. So it's exactly the same operation, the same effect as the multiplication in the reverse. So these multiplying and dividing machines commute when we multiply them together. Great. Of course, now we are not only dealing with these multiplying machines and not only dealing with these dividing machines, but also dealing with these combinations. And that is what a fraction is. It is take an integer here, consider it as the input of a copying machine, divide your input into that many parts and retain some other integer number of them. And now we have to deal with how these machines these fractions can operate among each other. How we multiply and divide them, and then how we add and subtract them. Then we have actually extended our range of what a number is to these fractions.